Okay, so we are going to talk about gas stoichiometry. I know you thought you got away from it, but it reels you right back in. A couple things with gas stoichiometry. We're going to make sure that we still use our ideal gas law because in stoichiometry we're converting from one substance to another, so we're going to need moles. And then the other thing that we're going to use is Avogadro's. So remember 22.4 liters is equal to 1 mole. So those are the two main ones we're going to use. I did put your R value table in here. Remember, liters, Kelvin, pressure can change, but the R value changes based on the pressure. So let's start looking at what we have. So it says, what is the volume of oxygen needed to react with solid sulfur to form sulfur dioxide? So just like in all stoichiometry, write a balanced chemical equation. Has to be the start. You have to start with the balanced chemical equation. So let's do that. Well, oxygen is solid, so we can, sulfur is solid, so we can just start with writing sulfur. Oxygen gas is O2, and sulfur dioxide is SO2. We should remember that we can write this as 1 mole of sulfur plus 1 mole of oxygen gas and 1 mole of sulfur dioxide. That's just interpreting the equation. But if we look at Avogadro's principle, they're kind of proportional. So you can also write this as 1 liter of sulfur and 1 liter of oxygen gas react to form 1 liter of sulfur dioxide. This little step is going to be very useful for this because it tells us that we have 3.5 liters of sulfur dioxide and it wants us to convert it to oxygen gas. Well, we know from the balanced chemical equation we have 1 liter of sulfur dioxide and 1 liter of oxygen gas, giving us a total of 3.5 liters of oxygen gas. So they're set proportional to each other. Let's try another one to make sure we understand that step. Again, making sure we know, gotta start with a balanced chemical equation. So, how many liters of propane will undergo a complete combustion reaction? Well, that's all we needed to know. Combustion reaction, propane. So we have C3H8 reacts with oxygen gas, and we know by now that the only two products when you have a carbon-based molecule undergoing combustion is carbon dioxide gas and water vapor. Okay, so we have that already totally completed. So now where do we go from here? Well, that's pretty simple. We just need to start with a balanced chemical equation. Okay, so let's put a 3 to make our carbon balanced on both sides. Put a 4 to fix that oxygen problem. And then we just add up our oxygen, which is 10 on this side, divide it by 2, and a 5 here will solve that problem. So in this case, we're just asking to go, so we start with 34 liters of oxygen, and it's asking how many liters of propane. Well, if we look, we have 5 liters of oxygen gas based on the chemical equation and 1 liter of propane. So then we would just solve to get 6.8 liters of propane. Again, remembering to interpret this as 1 liter, 5 liters, 3 liters, and 4 liters because they're completely proportional according to Avogadro's principle. That's under standard temperature and pressure, but what if things start changing? That's where the ideal gas law comes in. PV equals nRT. So in this one, it says determine how many moles of water vapor are produced by combustion reaction again with methane. So we start with that balanced chemical equation. And this time we should know we got to fix this. So this puts a 2 here, add up our oxygen, and now we have a 2. So now our chemical equation is balanced. This one gave us a lot of information. It told us our pressure is 1 atm. Well, that's standard, so that's nice. Which means our R value for this is 0.0821. Our temperature is 200 degrees Celsius, which means it's 473 Kelvin. And we have a volume of 15 liters. And it's asking us to find an N. And this N is for methane. We'll use stoichiometry after to convert, but right now we're going to find for methane using the ideal gas law. If nothing changed, we could just use Avogadro's understanding that everything is proportional, but it's not. Not in this case because we have changing. So N is going to be equal to PV over RT. So that gives us our 1 atm, 10.5 liters, all over our R value of 0.0821. Make sure that you're getting the right R value, 473. And so we get for N for this a 0.27 moles of methane. So now what do we do with moles of methane? Well, we already know that if we have 2.7 moles of methane, we can convert that into moles of water by using our balanced chemical equation. In this case, we have 1 mole of methane. We have 2 moles of water, which gives us 0.54 moles of water. Remember, this is the molar ratio that comes from the balanced chemical equation, so we should know where that's at already. And we're just using the ideal gas law to solve for this because we have varying temperatures or pressures. Those things are changing and they're not perfect. If they're at standard, we don't have to worry so much. We can just use Avogadro. So let's use this one now. So we have solid potassium metal will react with chlorine to produce an ionic potassium chloride. So let's just, before we even go to that next sentence, let's get that balanced chemical equation out of the way. Since it is a metal, potassium can stand alone. Chlorine is a halogen, which means it's always diatomic. Potassium is in group 1A, so it has a +1 charge. Chlorine is a halogen in group 7A, which has a -1 charge. So ionically, they form KCl. To balance this out, we put a 2 here for the chlorine and a 2 here for the potassium. And now we have our balanced chemical equation. So it's asking how many liters of chlorine gas are needed to completely react with 2.5 grams of potassium at standard temperature and pressure. Well, I said, hey, you can use Avogadro for standard temperature and pressure, right? Sure can. In this case, though, we have to take our 0.204 grams of potassium, and we have to convert it into a usable form. Oh, yeah, moles. So we're going to take it and turn it into moles. 39.1 grams of potassium is equal to 1 mole of potassium. If it's easier for you, because some of you might feel like 5 steps is too much, you can actually just solve and get 0.00522 moles of potassium here. And then we can go on to the next step. If you don't, I'm going to add on. Once I'm in moles of potassium, I can go to moles of chlorine using the molar ratio. I know that there are 2 moles of potassium to 1 mole of chlorine. From here, yep, you got it. Avogadro, 1 mole of Cl2 is equal to 22.4 liters of chlorine. multiply across the top, divide by the bottom, and you're going to get 0.0584 liters of chlorine gas, which would be 5.85 times 10 to the negative second liters of Cl2. And so just remember, if we're at standard temperature and pressure, 1 atm and 0 degrees Celsius, then we can use Avogadro's, because everything in the balanced chemical equation is comparable back and forth. But when we don't have it comparable, when there's a varying pressure or temperature, that's when we need to use the ideal gas law. And from there, we can transfer into moles. And for moles, knowing a balanced chemical equation, we can go anywhere.